This is degree 3 polynomial. There is a cubic formula, just like quadratic formula. So you have these coefficients, you put it into a formula, you just crank it, and there's the answer. So you can Google it, and it exists. But this is a very special type of polynomial. So we can solve it by hand. Maybe that's the first thing we should try, but not many algebra textbooks actually suggest this as the first method to try. But this is exactly the same thing as that mathematical homework. Will all of you be able to do that mathematical homework? Not really. So here's how it goes. That was a bit advanced problem. I think this is the simplest polynomial shape. And why not thinking about how do you solve quadratic equation if you don't use a quadratic formula? What's behind the quadratic formula? What method is behind the quadratic formula? Completing the square. So if you look at it here, what is the first thing you should try? Maybe a reasonable thing is you have to complete the cube, right? Why not? Try to complete the cube. Maybe it works. Because there are so many coefficients here, often it fails. But maybe it'll work. Seems like the first thing we should attempt, but not many textbooks actually suggested. You know, if you just pick a random cubic polynomial, there's no chance it's going to be perfect cube. So let's do that. Left-hand side is a z. Maybe I'm going to write it just like this: z minus z naught cubed plus maybe z1. Is that all right? Maybe it's possible. So it's not. Maybe it's not possible. So it's a question. Can we pull out perfect cube and left with just a constant term, right? If that's so, then you can see the left-hand side is a perfect cube. If you move that to the other side, it becomes a w to the n equals z1 form. Does that make sense? Okay, let's try that. So how can this happen? Again, it's a slightly different point of view. We're not actually deriving, add and subtract. Think about the procedure of completing the square. We're not doing that. We're just thinking about, is this possible? If this is possible, we should be able to determine z0 and z1. Not algebraic derivation. We just quickly find the z0 and z1. So who knows how to expand left-hand side, cubic part? Remember Pascal's triangle? So you're going to pick up third power, right? And you're going to pick up second power in the next term, and it picks up the first power of the other term. Z0, 1. What is the coefficient? Anybody remember the coefficient? It's 3, okay? Now, the power of z goes down, and z0 picks up the second power, keeping the sum of the exponent always what? The sum of the exponents always 3, right? What is the second coefficient? It's 3 again. And z finally disappears, and z0 goes to third power, right? Make sense? And plus, there is a z1 out there. Does that make sense? Okay. So we want this thing to be equal to the left-hand side. We want this thing to be equal to the left-hand side. This is what you see here, right? So z cubed, that's all right. What about by comparing the coefficient of z squared? What do you have? What do you get? This forces 1 plus I to be what number? That's from the left-hand side. Sorry about this, swapping this around. So I'm going to actually put left-hand side over here. It's less confusing. Left-hand side was really in the left-hand side, so I'm going to write it like this. Left-hand side over here, and I'm looking at the left-hand side, particularly the z squared. 1 plus I is the coefficient, right? What is the coefficient in the right-hand side? 3z0, right? Correct? And what do you get about possibility of this one? Here's 1 plus I divided by 3, right? If this cubic thing is going to work, z0 have no choice but to be 1 plus I over 3, right? Okay, so but we didn't do anything about z to the first and rest of the part. If this choice accidentally agrees with the 21 over 3, and we're good, we're lucky. If that doesn't agree, that means You cannot pull out a perfect cube there, right? So will you go ahead and compute next thing? So let me ask this question, will this work? I hope this question makes sense from what I said there. Do you know what to do to answer that question? Will this work? Well, I match the coefficient of z squared, right? And then I have no more control on coefficient of z. Constant term, I have an extra free variable there, right? But this coefficient of z is completely controlled. So to check will this work, what should I do? What should I compute? Jack said 3z naught squared. Can somebody answer that where this one come from? This came from where? Coefficient of what? Coefficient of z to the first, right? Coefficient of z to the first. And this is supposed to be equal to what number? Left-hand side, right? What's in the left-hand side? Is that silly? 21 over 3? Sorry about that, but there's a better way to write it. So see if that's really 7. I think I might have done that wrong. I don't see that. That could have been... Sorry about that if I made the mistake in there. That must have been... let me fix that. Alright, this was 2 times I, not 21. So everything's alright. So here we're checking that... where am I? Is this 2 times I, is this question, right? If this works, 3 over, right? If this works, it's great. Okay, so that's what you have to check. And I was almost doing that over there, so I'm going to stop asking question. So let's calculate 3 times z naught squared. What is it? 3 times z naught was here. If you square it is 9. So let's do that. What was that numerator? 1 plus I squared, right? That's 0, right? 1 plus I squared, and you're left with a 2i. So that's 3 and 2i divided by 3, correct? So what happened? It accidentally matched the coefficient of z, right? Right? That's good. So we got this controlled, lucky that matched, and we have to get the third coefficient. Is that right? So let's try that. Good. We were lucky. And what's the next equation to consider then? Z naught cubed plus z1 supposed to be what number now? 1, right? Okay, so you can see we have a free variable z1, so it's no problem, right? You don't have to worry about anything. z1 is completely free to determine. Okay, so let's calculate that. So that is what we want to make this one identically equal to that general form. So what's z1? 1 minus z0 cubed. And I will use z squared. What was the z0 squared? We already calculated z0 squared was 9, 2i divided by 9. Is that right? 2i divided by 9. So that's a z0 squared part. So we can do a little bit of work for cubic part. So what is in that? 3 and 1 plus I times 2i divided by 9. From here, if you use Mathematica, it will be a lot more efficient. You know, just can do the arithmetic quickly. But let's just finish this off. And 27, right? So here's a 27. What is it? Minus plus 2 minus 2i. Would you agree? 2i is there, negative 2i, and 2i becomes a positive 2. It's a 29. I think I've seen that number when I was preparing this one. So something like that, right? Make sense? Okay, let's go back. What we have discovered now is that that cubic polynomial, which I'm going to just copy, not equation, just that cubic polynomial there, is identically equal to z plus what number? Z naught, who's 1 plus I divided by 3 to the third power, right? A plus what number? 29 divided by minus 2I divided by 27. Okay? You go Mathematica and you type in the right hand side and expand it. You use command expand and you will verify that this is the same thing, identical the same thing, right? So what's the advantage of the right hand side? Why did we do all that? So that we can use this method. The equation, if you make a substitution, it becomes w to the third equals something. So do you see how it goes? So what's w? W is going to be the entire thing underneath the third power, right? Under that substitution, what are we going to prove? What are we going to solve? Is w to the third equals what number now? Negative, you see that? That goes to the other side if you set that one equal to 0. Correct? Negative 29 minus 2I divided by 27. Right hand side, using the Mathematica, you can, since the number is ugly, you can use, you can calculate modulus, right? And you can calculate argument, and you can do divided by 3 business. Make sense? All right, so let's go ahead and do, all right, from here, what we're going to calculate, absolute value, modulus of this number, divided by 27, whatever that one is, and then we're going to calculate arc10 of what number? 27 is a common denominator, right? For a real part and imaginary part. So what would that be? I see positive 2 as an imaginary part, ignoring 27, because that will cancel out. How about the other one? Negative 29, right? It's negative 29. This will be the first quadrant or fourth quadrant. But which quadrant is this one in? Negative real part and positive imaginary part, right? Is that correct? Negative distributed. So it's in the second quadrant, is that right? Second quadrant, what do we do about this arc10? Add pi. So that's our argument, and it is actually the principal argument, right? Because that's exactly, negative side is on the fourth quadrant, so if you add pi, it goes to the, I think it's really the principal argument. Although it is not necessary to use the principal argument to handle w to the n equals z naught. Do you agree? It is not necessary to use a principal argument to handle this equation. Whatever you prefer, and that'll give you 3 different solutions or 7 different solutions. It'll give you those solutions. Polar form has many different ways to express it, and that was the deal. Okay, so from here, I think it's kind of clear, right? We repeat the same procedure. Then you get how many w's? You get w0, w1, and w2. Is that right? So you're going to have the 3 solutions. That's not the answer, right? How do you finish off the answer? Your z naught, z0, that's a bad notation because I use the z0 for something else, but I hope this doesn't confuse you. That's not the same z naught. So what is it? You have w0, right? You see what to do? This is the connection. We solve for w, you want z's, right? So let me just change to z's so that it's not confused about that. Z can be w0 we have there, and what do we add? If I have w to solve for z, you have to subtract that number 1 plus I 3, right? Over 3. So if you subtract that 1 plus I over 3, that's how the w and z's related. You got w's, what's z? Go back to substitution and solve it like this. Second one, w1 minus the same number, w2 minus 1 plus I divided by the same number, right? So you define this one as a list and go back to Mathematica, use the map function in Mathematica. You just map it into all that. You're supposed to see 0, 0, 0, 0, right? But Mathematica might give you 10 to the negative 16 kind of approximation. So you can check your answer with the Mathematica in that way. All right. So completing the cube makes sense. It worked because I generated like that, and you're supposed to, that's one probably method we should try. If that doesn't work, then grouping and rational zero theorem is usually the technique that we have for degree 3. All right? However, but if you happen to have, there are other techniques. There are other techniques that I just said those methods. But there are these examples. Z cubed plus z plus 1 equals 0. This one, if you try rational zero theorem, 1 is the only thing you're going to try, and negative 1 is the only thing try, and you will quickly realize it does not have rational zeros. Do you know rational zero theorem? Just like the quadratic polynomial, you look at constant term and the leading term. Think about all combination that involves whole number factors. And eventually you fail for that kind of thing. You can imagine I can write down a quadratic polynomial, for example, like this, and 2x squared plus x minus 5 equals 0. If you try to factor this one, you're not going to see any easy factorization. But you can still factor this, right? Using the radical symbol. It's the same thing. That does not have nice rational zeros, so you have to find 1, 0, real 0, using a find roots command and approximation, however you do it in Mathematica can do this one. And then you have to factorize. So this one has exactly 1 root, real root. Can somebody explain that, why this one has exactly 1 real root? Not going to the Mathematica and sketch it. There's a nice way to do this. First of all, degree 3, you agree there is at least 1? Because the degree is odd, you know that n behavior pointing opposite direction, it's going to cross it. Intermediate value theorem. Some of you answered very nicely in the probably first homework. So it's going to cross. How do you show that it cuts exactly 1 time? This polynomial happened to be increasing function, right? If it is always increasing, once you cut, why would you come down and hit it again? It keeps rising. So how do you prove it's increasing? What calculus method do you know to show something is increasing? Derivative being positive. Do you see the derivative being positive? 3z squared plus 1. Isn't that a positive number, right? Therefore, it just keeps going on. So we can rigorously prove that exactly 1 root, right? And that is called alpha, whatever the numerical approximation is. You can probably do it by hand to pinpoint roughly where it's located. Now, do you know the rest of the part? If that's called alpha, how is it going to look? Right? It's going to be a factor. If you have a 0, that becomes a factor. Okay? That is called the factor theorem. So if you do divide this polynomial by z minus alpha, what will be the remainder? If you do the long division of this polynomial by z minus alpha, if alpha is the real root, what will be the remainder of this thing? 0. That's what it means, it's dividing, right? If 7 divides 28 or 21, then it means if you divide 21 by 7, the remainder is 0. So z minus alpha being the 0 being a factor here like that, so it's going to be the quotient. So you can get this one through long division, right? Or synthetic division. But here's how you combine this. You're going to multiply whatever the coefficient of z and the constant term, right? Think about comparing it. You see that z squared term in here? I don't see any z squared term in the left-hand side, right? You? No. So how do you get z squared here? If I multiply these two, I get z squared, correct? what else combination from each of the factor you multiply to get a z squared? Multiply z with another z over there, right? And this is the only two ways, right? There's no other. This is only two terms. We use them all. So that's all that's going to be. So what is supposed to happen between the z squared and z squared? They're supposed to cancel. I don't see any z squared in it, right? This is a negative alpha coefficient. What should be that? Positive alpha. So that z squared, negative alpha, and positive alpha z squared, they multiply, cancel out. That's the only possibility. How to figure out this constant term? Two ways. Only way to get a constant term is combining the constant terms, right? That's the only way. Or you can just go by next one. How about coefficient of z? It's 1, right? So how do you get z coefficient in here? Z is multiplied to this constant about to be determined. How about this one to multiply to where? That coefficient, right? Then you get z, and there's another way to get z, right? So I get, from there, I get negative alpha squared as a coefficient of one part of z, right? And this one is supposed to be just 1 together, right? So if I kill that by positive alpha squared, and if I do that, it's going to kill that alpha squared, right? But I still want that plus 1, so I can add 1 there. So if you multiply z, I get alpha squared z. That's going to cancel the other one. And I have additional copy of z that matches that one. So this is what you're going to get if you apply long division or synthetic division with alpha as a letter. Just, execute that, and this is what you're going to get. But let's compare with what we had before. How about these two things? Negative alpha times alpha squared plus 1. Isn't that supposed to be 1, the constant that we didn't take into account when you figure this one out? So let's see what result we have in here. What does that mean? Negative alpha cubed minus alpha equals 1. Is that right? Is this really true? If it is not true, something went wrong, right? It should agree that remainder 1. If I move it over there, alpha squared plus alpha plus 1 equals 1. Why is that true? Because alpha was the 0 of that polynomial. Alpha cubed plus alpha plus 1 is 0. If you really use this numerical value, you can see that constant term turns out very, very small quantity. Does that make sense? That real root part takes care of this one, so no contradiction. So this is z minus alpha. You can get approximate value. Now this is a quadratic, right? What's the beautiful part about the quadratic polynomial? You can always complete the square, right? But it's already worked out. Many of you already know quadratic formula. Is that right? Yeah. So I have one real roots. And this is degree 3. At most, they have 2 solutions, right? 2 more solutions. What does the fundamental theorem of algebra says? Right, exactly, and solutions. Right, we have 1, so we have 2 more in a complex number, and they're coming from this quadratic equation. Is that right? So we got one real solution, and we look at z squared plus alpha z, alpha squared plus 1. Although we have a numerical value of alpha, no point of keeping it this way. I think is better. Okay, and whenever this is another convenient. Whenever you have alpha cubed shows up, you can replace it with a negative alpha minus 1, right? Whenever alpha cubed shows up when you're calculating, you can replace. That's the algebraic property of alpha. So how do you solve this equation? What is that we just talked about? Quadratic formula, right? Think about it. When you do the quadratic formula, all you do is that we have letter A, B, C, and do algebra. That algebra makes perfect sense with the complex numbers, right? So without going through the proof of quadratic formula, I hope you believe all that it is an algebra in there, and we have well-working algebra in the complex numbers, so no need to repeat this again. Just apply the quadratic formula. So what are those z's? What's in the denominator? 2 times a, which is 1 here, right? Negative b, right? What is negative b here? Negative alpha, correct? And plus minus square root of b squared, right? B squared is alpha squared minus 4 times a is 1 and c is alpha squared plus 1. No problem having 2 in the denominator, no problem, right? Negative alpha out there, no problem. Only problem is that what is this root symbol in there? So I'm going to pull out 1/2 out there and negative alpha and plus minus square root of what do you have in there? Alpha squared minus 4 times is that, let me just simplify the negative 3 alpha squared, right? Minus 4. Did that just right? Okay. All right. If you look up your old algebra textbook, or when you are assisting those students who are learning the very basic algebras, you have a tendency to pull out the negative in there outside the square root, right? If you look up those books that summarizes how to simplify the radical, they always have a condition to manipulate this product of the radical. There are conditions that whatever is involved must be positive numbers. If you just freely pull out this negative, you might end up with some sort of contradictions. It is not contradiction because those rules have a little condition and students, even beginners, have tendency to ignore. Okay? So we're not going to pull that negative outside. We're going to leave it in there. And actually, no, I was wrong. If this alpha is a complex number, I would definitely do that. But I know alpha is a real number, right? Therefore, I know the sign of this one. Therefore, I can do that. If alpha is a pure, some sort of complex number, you cannot pull the negative outside, right? But I know this is the negative number. Alpha squared is positive, negative 3. You have, even if it is not squared, and because you have a numerical value, you know completely whether it's a positive or negative. Therefore, you can turn that into complex number I easily. Okay? But if alpha is a complex number, you have to be careful. The cube root, and you did it in test, that's what you have to do. Square root of 1 plus I. Then you have to go through the w squared equals 1 plus I, that method. But here it's easy. So 1/2. What is it? Negative alpha and plus minus. Isn't that 3 of the root? 3 alpha squared plus 4 is a positive number, right? Negative, pull that outside. What's the better name of a square root of that negative one? Then imaginary number I, right? So this is the complex solution. Real part, imaginary part, nicely separated out like this. Does that make sense? All right. This is the polynomial equation, and this is the most basic functions in the world, right? Add and subtract and multiply, not even dividing the function in the denominator. So we start with like this. So this looks like basically algebra solving equations, right? But what's the title of this course? Title of this course is Functions of a Complex Variable. So I hope you see this as more of the function, polynomial function, and that's the more important part. Let me introduce one more important proposition. So since we have done this much of a polynomial algebra, they introduced 2 more things, but I think this one is more important than the other one. I'm not going to do the other one. Maybe we'll do so at some point, but not right now. Here's a proposition. I'm looking at the polynomial. What does a fundamental theorem of algebra say again? Every polynomial is completely factored. It has all the zeros in there, right? It's completely factored. Zeros is the factors. So you can view the polynomial in this form. We have, let's say, I'm just going to use your example, degree 5 polynomial. And it's going to factor like this, right? By what theorem? Fundamental theorem of algebra. No matter what degree 5 polynomial you have, as long as it's monic, the coefficient is e to the 5th, it's going to look like this. If it is not monic, then you can factor out that polynomial outside there, leading coefficient. So Do you know what happened if you expand it? First thing is going to be z to the fifth, right? How do I get z to the fifth? The principle of expanding this one is to choose one term here in the first factor and choose another term in the second factor and all the way up to the fifth factor there. There are two choices from each of them, right? And you choose them and multiply all out 5 times, all 5 factors. That's how it is. So if I choose z, second factor z again, all the way to the fifth factor, you select z all the time, and if you multiply all, you get z to the fifth, correct? Let's go to z to the fourth. So we're going to select each of them and multiplied number of copies of z was 4 times. Okay, 4 copies. So one of them, for one choices, we're not choosing z, but we're choosing zk, right? That's why. So if I choose this one, z1k, negative z1, and all the rest of the part, I'm choosing z, right? How about choosing from the second factor, I choose negative z2. All the other factors, I choose z. If you multiply those, you also have z to the fourth copies, right? Okay, so I see this copy shows up, and that copy shows up, right? If I choose in the third factor the constant term and all the other thing is z's, you give another z factor, things like that. So who wants to volunteer? Shape of the coefficient of a z4. There's negative all the time. You know what goes in there? We'll keep adding this type of numbers, right? Okay, z1, z2, plus z all the way to the z5. Does that make sense? Yeah. If you actually collect this coefficient of z to the fourth, and this is what you can have. Okay, let's apply the same principle to z to the third. So how can you end up at z to the third? How many constants do you have to choose from when you go through 5 factors? 2. So that remaining 3 times you have to pick up z, so you end up z to the third. Make sense? So what is the first thing that comes to your mind? That how do you get z to the third? And what was one term? Maybe I'll choose z1 and z2, the rest of the part. Then is that positive z1 and z2? Because negative z1, negative z2 multiply becomes a positive z1 and z2, right? So I'm going to actually write them all out. All right. So 2 of the constants, that's automatic. So z1 and z2. Well, there are many different ways to ordering this thing, right? But maybe you can stick to z1 and go through z3. Stick to z1 again and go through z4. Stick to the z1 again and go through z5. Right? Make sense? But it's not it. Now you can stick to z2. You don't have to z1. We already did z1. And think about it. There's no repeat once you choose it. That's a unique places that identical. So that next thing that you should consider z2, z3. Right? You see the pattern? Indices is like 2 indices always in increasing order. Think about all the possibilities. So what is the last one that you would be writing? z4, z5. Is that right? Okay. Now who can explain the number of terms that is involved in there? It's the same principle. The principle of choosing 2 numbers out of 5 choices, right? So 5 choose 2. Do you know those things? 5 choose 2. You have 5 spots. You have to choose 2 of the spots where you select constant, not z, right? So this is called 5 choose 2. Isn't that exactly the coefficient of binomial coefficients, right? And their number of terms. So if all the z1 through z5 are equal to each other, this will be z minus z1 to the 5th power, right? And all that thing is just z1, 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 and that coefficient picks up exactly the number of elements in there. So 5 choose 2. Do you know how to calculate those? 5 choose 2? So you start from 5 and you start from 1. 2, you go down 2 steps, 5, 2, and 1, 2. And that's how you calculate it. Okay? So how many terms are there? 10 terms are there? That's what that is. Same Pascal's triangle, just like some of us were able to write down 1, 3, 3, 1. It's the same thing. Okay? So what is the third one? Who'd like to volunteer of the second power? And then I think it's going to be clear then how it goes. So here is the beginning of the second power. Who wants to do that? What's the sign this time? Choosing 3 constants, 2 z's, right? What is it? Negative. So what is the first one that comes to your mind? z1, z2, z3. What is the last thing come to your mind? 3, 4, 5. That makes sense to me. So how many terms are here? In binomial language, binomial coefficient language is 5 choose 3. There are 5 spots, 3 spots we're choosing. How many ways do we do that? So this is 5 times 4 times 3. Go down 3 steps. You're going up 3 steps. This is how you calculate, right? That is 3 cancels. That happened to be exactly the same before. And there's some property to that. And so on, right? So this is how the shape of the coefficient look like. If you have 5 things multiplied, I think it's a very simple principle, right? Add those. All right, so here's an exercise. Two times z to the 5th plus z to the 4th plus z minus 1 equals 0. That's a polynomial equation, and don't try to pull out the perfect fifth. It's missing some terms, right? You can anticipate it's not going to work. And so here's the question. So, well, first of all, how many solutions does it have in complex? Exactly 5. Some of them could repeat, right? So when we say sum of all the roots, we usually count multiplicity. If there are 2 repeating, then we add 2 plus 2. So the sum of all the roots. What is it? You know, the sum of all the roots nicely shows up in front of some powers of z, right? We've seen that in here. We don't know what those zeros roots are, but they showed up as a coefficient, right? Which coefficient? Z to the 4th. In front of z to the 4th, you will see this number, right? Right? That number is exactly the sum of all the roots. Opposite sign, because of the negative picks up. So we don't know what that is, but we know what those roots are, but we know the sum easily from the general form. But this is not monic. You can see the coefficient of z to the 5th is 1, right? But this is not so. So what do we do? How can you pull out an equivalent equation, meaning that it has the same zeros? Divide everything by 2. It's 1/2. What about this one? 1/2 again. And this is 1/2, right? Now it looks like a monic degree 5 polynomial, and you know this 1/2 is supposed to be what kind of thing? The negative sum of all these 5 solutions. Is that right? No matter what, it's going to factor into 5 products, and this is how it works, right? So what is the sum? Negative 1/2, right? Negative 1/2. We don't know all individual solutions, but sum is supposed to be negative 1/2. How about the product? Do you know the product of all these? Sum is in front of z to the 4th. Where do you think is a product is here in this pattern here? We didn't work out every coefficient. I stopped it because you understood it. Where do you think this product shows up? This was the negative sum. Is that right? How about product? Don't you think it's a constant? If you look at it here, the constant part have all the product, and that's the only way to get constant term. So that one is the product. But is that going to be plus or minus? If you multiply these 5 zeros, are you going to pick up positive sign or negative sign in front of the product of z1 through z5? Negative, because you're multiplying 5 times, right? So it's going to be negative. Here we use the 5. Here we didn't use 5. It's always negative sum, right? But product, if the degree is even, you're going to pick a positive product. If degree is odd, you're going to pick a negative product, right? That's one thing. So also free, what is the product of these things? Is that positive 1/2? Correct? That's the meaning of the coefficients. I will not go over the rational zero theorem, but some problems in the book give you a polynomial like this, ask you to go through rational zero theorem, discover rational zero on your own. Okay, so they have nice example, and you can study, and from that you will probably recall what that rational zero theorem is. But that's the most general techniques that is available and out there. Otherwise, factoring polynomial is as difficult as factoring large prime numbers. All right, if you think about it, that's exactly the same problem. All right.